Science is often described as a collection of facts. Planets orbit stars, diseases can be caused by microbes, matter is made of atoms, societies change over time. But science is more than a library of conclusions. At its core, science is a disciplined way of building knowledge. It asks questions about nature, people, and the world around us, then demands that the answers be testable. A claim is not scientific simply because it sounds technical or comes from an expert. It becomes part of science only when it can be examined against evidence, challenged by others, and either supported, revised, or rejected. The engine behind science is the scientific method. In its simplest form, the process begins with observation. Something happens, and someone notices a pattern, a puzzle, or a contradiction. From there, scientists form a hypothesis, a possible explanation that can be tested. Then comes evidence. That evidence might come from an experiment, a field study, a survey, a telescope, a microscope, or a mathematical model connected to real measurements. Finally, scientists draw conclusions, but those conclusions are never treated as permanent truth. They are judged by how well they explain the evidence and how well they survive further testing. This testable quality is what separates science from many other ways of thinking. A scientific idea must take a risk. It must be possible, at least in principle, to discover that the idea is wrong. If a claim can explain every possible outcome after the fact, it may be interesting, but it is not very useful scientifically. Strong scientific explanations make clear predictions. If germs cause certain infections, then blocking germs should reduce disease. If a planet exists beyond the range of direct sight, its gravity should disturb nearby objects in measurable ways. Science advances because it does not protect ideas from failure, it exposes them to failure. Science is also a community effort. Individual scientists make observations, design studies, and propose explanations, but their work enters science through a wider process of criticism and validation. Other researchers inspect the methods, repeat the experiments when possible, compare results, and look for alternative explanations. This can be slow, competitive, and imperfect, but it is essential. The goal is not to trust one person's authority, but to build knowledge that can withstand independent scrutiny. Over time, reliable findings are organized into theories, models, laws, classifications, and shared bodies of knowledge that become the foundation for new questions. Modern science is often grouped into major branches. The natural sciences study the physical world, physics investigates matter, energy, forces, and motion, chemistry studies substances and reactions, biology explores living organisms, astronomy examines the universe beyond Earth, geology studies the planet itself. These fields differ in tools and scale, but they share a commitment to evidence from the natural world. A physicist working with particle accelerators and an ecologist studying forests may seem far apart, yet both are trying to explain observable patterns using methods that other investigators can examine and test. The social sciences apply systematic investigation to human beings and societies. Psychology, sociology, economics, anthropology, political science, and related fields examine behavior, culture, institutions, decision-making, and social change. Studying people can be especially complex because humans interpret, adapt, and respond to being studied. Controlled experiments are not always possible or ethical, so social scientists often combine surveys, interviews, statistics, historical evidence, fieldwork, and natural experiments. The aim is still scientific, to move beyond assumptions and anecdotes toward explanations that are supported by evidence and open to criticism. Some fields are closely connected to science but are usually treated differently. Mathematics, logic, and theoretical computer science are often called formal sciences. They are powerful because they use deductive reasoning, starting from definitions, axioms, and rules to prove conclusions. A mathematical proof does not need a laboratory experiment in the same way a biological claim does. Yet the formal sciences are deeply woven into scientific work. They provide the language of measurement, probability, modeling, and computation. Science often needs mathematics to express ideas precisely, but mathematics itself usually does not rely on the scientific method as its main source of truth. Applied sciences use scientific knowledge for practical purposes. Engineering applies physics, materials science, and mathematics to build bridges, aircraft, computers, and energy systems. Medicine applies biology, chemistry, statistics, and clinical research to prevent and treat disease. Agriculture, environmental management, public health, and many technologies grow from the same pattern: understand how the world works, then use that understanding to solve problems. Applied science shows why scientific knowledge matters beyond curiosity. It can become clean water systems, vaccines, safer buildings, weather forecasts, medical imaging, and communication networks. The roots of science stretch far back into human history. Long before modern laboratories, ancient civilizations in Egypt and Mesopotamia developed mathematics, astronomy, medicine, and record-keeping. Their knowledge helped people track seasons, manage agriculture, design buildings, and treat illness. These early systems were not science in the modern sense, but they were important predecessors. They showed that careful observation and organized knowledge could make the world more predictable. Later, Greek natural philosophy tried to explain physical events through natural causes rather than only myth or tradition. That shift helped prepare the ground for more systematic inquiry. Scientific knowledge did not develop in one place or in a straight line. Indian scholars made major advances, including mathematical ideas that helped spread the Hindu-Arabic numeral system. During the Islamic Golden Age, scholars preserved, criticized, expanded, and transmitted knowledge in mathematics, astronomy, medicine, optics, and philosophy. They built observatories, translated earlier works, and produced new investigations of their own. These contributions later entered European scholarship, especially through translation and exchange. The history of science is not the story of one civilization suddenly discovering reason. It is a long, interconnected process of borrowing, refining, challenging, and transforming ideas. During the Renaissance, European scholars recovered and absorbed Greek and Islamic works, reviving natural philosophy. But by the 16th and 17th centuries, something more dramatic began to happen. The scientific revolution changed how knowledge was pursued. Thinkers increasingly relied on observation, measurement, experiment, and mathematical description. New discoveries in astronomy, physics, anatomy, and mechanics challenged older assumptions inherited from classical authorities. Instead of asking only what ancient writers had said, scientists asked what nature itself revealed when carefully observed. This did not create perfect science overnight, but it shifted the center of authority from tradition toward evidence. By the 19th century, science began to look more like the organized profession we recognize today. The phrase natural philosophy gradually gave way to natural science. Universities, academies, journals, laboratories, museums, and specialist societies became central to research. Scientists developed more specialized roles, shared standards, and professional identities. This mattered because science depends not only on brilliant ideas, but also on institutions that preserve data, train researchers, fund investigations, and communicate results. Modern science is built through networks, people, equipment, publications, grants, conferences, and archives all working together to make knowledge cumulative. Today, scientific research is often highly collaborative. Major projects may involve teams across universities, government agencies, research institutes, hospitals, and companies. A climate model, a particle physics experiment, a vaccine trial, or a space mission can require thousands of people and years of coordinated work. At the same time, individual curiosity still matters. Many breakthroughs begin with a researcher noticing an unexplained result or asking a question others overlooked. Science is driven by both wonder and problem-solving, the desire to understand reality and the need to respond to disease, energy demand, environmental change, infrastructure, and security. The power of science creates responsibility. Discoveries can lead to medicines, technologies, and public benefits, but they can also raise risks and ethical questions. That is why societies develop science policies, rules and priorities for funding research, regulating products, protecting health, managing the environment, and guiding defense or commercial applications. Science does not answer every moral or political question by itself, but it gives decision-makers stronger evidence about consequences. In the end, science is not a finished monument of facts. It is a living method for testing explanations, correcting errors, and expanding what humanity can reliably know. If you found this helpful, please like this video and subscribe for more explainers.